Okay, good evening, everyone. Welcome back to RoboCup at Home Education online classroom. And today we are entering the fourth class for the open platform online classroom. I'm Jeffrey from At Home Education. Together with me today, we have our sponsor and technical support, Jupiter Robot, and also our LOC from Thailand. So we are going to start very soon. Okay, so let me operate the slide. Okay, so this is the arrangement for today. So similar to the previous week, so we divided into two sessions. So the first session, the first hour, we will talk about SLAM map building. Okay, so today we'll talk about robot navigation, how to move your robot around, okay, for the mobile robots. So the first part is how to build the map, okay, using SLAM, simultaneously localization and mapping. So once we build the map, we also understand what are the software that we use and a little bit about the concept behind. Okay, right. Then for the second part, we are going to use the map and make the robot able to move autonomously. Okay, so it's the autonomous navigation, and this one including how to use the map to set the location, localization, and also to set the target so that the robot can do path planning and then start to move according to the path plan and also do like dynamic obstacle avoidance. All right, so basically that is the outline for today. And also very happy today that we have Jupiter Robot, so which means we are going to do this robot navigation. Ideally, we will like to do it on the real robot, okay? But because this is an online classroom, so we will use our online tools, which is we'll do our simulation platform to do the explanation of the navigation system. But because we have Jupiter Robot today with together with us today, so I hope they're able to do the real robot navigation later on, okay, to show you how we do things in simulation and also in real world. Then we can do some comparison, and that is I think it's a very cool demo that we can look forward today. Okay, right. So as people are still coming in, I hope we will settle down very soon. Okay. So for any newcomer, I'm not sure if any newcomer today. So for any newcomer, welcome to RoboCup at Home Education online classroom. Just a brief explanation about this class is like you can go to the first link on the slide, which will have all the details of the online classroom arrangement. Okay, not just today, but also we have other classes in other languages as well. So you can go to the website and see the detail, what are those classes and also the arrangement, what is the time and so on. Okay, regarding the meeting link, so I put up the QR code. We will use the same QR code for all the classes, for all the session as well. So which means this week, last week, and also the following week, we are using the same meeting link. So just remember this meeting link and come at the time of the class, then you can enter. Okay, right. So and for you guys who haven't signed up for our course materials, so the materials that you see in front of you, and also the past week video recording, just in case you miss any of the classes that you might want to do some revision. Okay, you can hit to the second link, which is our course material. You just need to sign up an account, log in, enroll in the free class. So those are the free classes, free courses. Then you can access the materials that we presented during our online classes. Okay, right. And lastly, if you have anything you want to discuss after the class, okay, of course, during the class we can discuss, and you can we actually have Q&A. And I will ask you, like, if you have any question, then you can turn on your mic and we can interact. But after the class, if you got anything you want to discuss, yeah, feel free to use the class group, okay, for any discussion. Right. So finally, I would like to once again remind everyone that for your privacy, please refrain from turning on your camera and also microphone during the class. But we will have Q&A time, and also as time, I mean, like along the class, we will give you chances, okay, for you to ask. And also today our LOC from Thailand is with us. So for any of you who would like to speak in Thai, yeah, don't worry and just feel free to speak in Thai. Okay, so you can ask question in Thai and our local organizing committee will help to answer you. Okay, so I hope you can join. And also if you cannot follow any parts because of the languages and so on, yes, feel free to ask, and yeah, our LOC will try to help you, okay, in terms of language support and so on. Right, so that is the arrangement. I would like to start now, but can I have our LOC? Because I'm not sure. Today we have quite a number of attendees from Thailand. So maybe I can invite our LOC to actually give some brief explanation about what I just said.
Hi, Jeffrey.
Okay.
สวัสดีครับทุกคนก็สำหรับคลาสวันนี้เนาะก็เป็นคลาสที่4แล้วนะครับสำหรับตัวที่เป็นat home นะครับที่เป็นRoboCup เนาะก็คือในส่วนของวันนี้เนี่ยจะมี2หัวข้อหลักนะครับก็คือเป็น SLAM Mapping SLAM Map Building กับ Autonomous Navigation นะก็คือเป็นในพาร์ทของการให้หุ่นเนี่ยสามารถที่จะเดินทางไปในจุดที่เราต้องการได้นะครับโดยที่หากท่านใดที่เป็นผู้ที่เพิ่งเข้ามาใหม่เนาะไม่เคยเข้ามาก่อนนะครับก็มีบรีฟคร่าวๆก็คือมีลิงก์ด้านล่างนะครับลิงก์แรกนะครับก็เป็นลิงก์สำหรับการเข้าถึงตัวข้อมูลต่างๆนะครับของClassroom นะครับไม่ว่าจะเป็น Schedule หรือว่าข้อมูลต่างๆนะครับสามารถที่จะเข้าไปดูได้ที่ลิงก์แรกเลยนะครับในส่วนลิงก์ที่2เนี่ยจะเป็นส่วนของ Course Material เนาะก็คือไม่ว่าจะเป็นสไลด์ที่ท่านเห็นอยู่บนจอนี้หรือว่าคลิปวิดีโอที่ท่านสามารถดูย้อนหลังได้นะครับแล้วก็ในขณะนี้ที่เขาอัดคลิปอยู่นะครับก็สามารถดูย้อนหลังได้ที่ในส่วนของ Course Material นะครับแล้วก็สุดท้ายเนี่ยหากท่านใดมีคำถามหรือว่าไปลองทำในวันอื่นๆที่ไม่ใช่วันที่เรียนแล้วมีคำถามเนี่ยก็สามารถที่จะโยนคำถามเข้าไปในส่วนของ Class Group ที่เป็นลิงก์สุดท้ายได้เลยนะครับแล้วก็หากท่านใดที่มีคำถามที่สามารถถามได้ในวันนี้ก็สามารถถามได้ในส่วนที่เป็น Q&A session เนาะแล้วก็สำหรับ Meeting Link เนี่ยจะใช้ Meeting เดิมนะครับสำหรับทุกๆคลาสหลังจากนี้นะครับก็ขอให้เข้ามาให้ตรงวันแล้วก็เวลาที่กำหนดครับก็จะได้เรียนคลาสที่ถูกต้องOkay, Jeffrey.
Okay, thank you. Right, so let's begin the class. Okay, so first, just to tell you what we need to get ready, and also if you have this thing, please get ready to follow the class together, okay? Because we would like to do the hands-on together. So today we'll talk about robot navigation development system, and mainly I will show you the demonstration in simulation. But later on, I would like to invite Jupyter Robot to show you the real robot as well. Okay, so we will try to do the comparison between the simulation and the real robot. But for you, in order for you to do the practice, okay, so you will follow me to do the development in simulation. Okay, and today is very simple because all you need to do is just your computer, right? Or your development environment. Okay, whether you're using Robot or whether you're using virtual machine, VirtualBox, VMware, everything is fine. And also for those who have signed up the virtual desktop of Robot for All, yes, you can use the virtual desktop for today's exercise, okay? And later on, I will use our virtual desktop to show you the simulation as well. So yeah, it's totally fine. So you can use any of those. But for virtual desktop, I would like to clarify here, if you are using the web base, it is not possible because like it is not able to run fully the RVs, the Gazebo, sorry. But if you have signed up for the beta tester, yes, with the RDP access and RDP access, you can use the virtual desktop to run fully the robot navigation. Okay, so it is basically the same as how you do it on your local machine. Okay, it's the same. So all you need to do is prepare your laptop computer with the development environment, which is Ubuntu, ROS, and today we will use the Gazebo mainly to show you the simulation model, and then we will use the ROS to do the navigation. Okay, but also if you have the robot or you plan to build a robot and so on, yes, the example that we show you, we can actually run it on the real robot. Okay, so later I will invite Jupyter Robot to show you how the same set of tools can actually use it on the real robot and also in the simulation. They are actually using the same software, and the operation is almost 80 to 90% identical. Okay, right. So later we will see, and we will do some comparison between the real world and also the simulation for robot navigation. Okay, so these are the things that I wish you to get ready now. Okay, so that we can do the class together. Okay, so for robot navigation, I will divide into these two sections, as I said just now. So we start with the map building, slide map building. Then after that, we'll talk about the navigation. So we first build the map first. Then only we discuss how to use the map for navigation, which is, but before we start, I would like to explain a little bit, okay, the concept behind how to build the map and also how to do the navigation. So first thing is like for mobile robot, because like this navigation mainly is coming from mobile robot. So which means when you want to do the robot navigation, all the development, all the research, R&D and so on, they coming from the domain of mobile robots. Okay, and for mobile robots, as the name also said, the important thing is the mobility. Okay, so for mobile robot, the mobility is they have various way. Okay, so for robot, they have various way to move around. Okay, you can find like legged robot, you can find like two-legged or multi-legged. You can find wheel robot with wheels, with track, with omnidirectional wheel, and also some they have like clawing, climbing, and so on. And also, of course, we have flying today. Okay, for example, like if you have a DJI or any drone, then yeah, it's flying. Okay, so any robot that can move around is categorized under mobile robot. But for today's class, the navigation, we mainly focus on ground robot. Okay, of course, the tools and also it can be how to say, expand into 3D. But today we are going to do just 2D navigation. So which means it's like we assume it's a flat surface and the robot's supposed to move on the ground. But of course, you can apply for legged robot or track robot or omnidirectional wheel robot, it doesn't matter, okay? You can use almost the same tools for those kind of robot as long as it's moved on a flat surface 2D. Okay, but you need to know how to create the locomotion model in your simulation, okay? Or else, if you're, for example, you're using a legged robot on a real robot, you can actually use the same navigation tools for map building, because the map building is almost the same, no matter what kind of wheel or what kind of, it's just that you need to input the correct model and then it should work. Okay, so over here, important thing, the message that I want to convey here is like, for robot navigation, today we are talking about 2D navigation, flat surface. So our map is also in 2D form. Okay, so if but these two can be extended into 3D, into other as well. Okay, it's just that you need to know as you increase your complexity, then you need to know how to manage, for example, your robot model, and also you need to know how to, for example, like from a 2D slam, you want to do a 3D slam. Okay, right. Okay, then just now I said, like, when we want to build a map, we need to know the robot model, for example. So basically how the robot move, you need to have the model so that you can do the modeling in order to get your, for example, mapping. Okay, because we will move the robot, and as the calculation involve the wheelbase design and so on, so that we can get some information that will be used to estimate the map, okay, to estimate the mapping based on the sensor data. Okay, and particularly in today's example, we will talk about the differential drive. Okay, differential drive means you have two wheels in parallel, and this is the most, how to say, simplest form of wheel design in mobile robot, because you only have two control parameter, which is left wheel and right wheel, and then either you turn forward or turn backward. Okay, if you have different direction in both wheel, then the robot will spin. Okay, and so on. So this is the simplest form. So we use this simpler form, and also the reference robots in our class also. For example, like the Jupyter robot is also, or the Turtlebot. Okay, so if you're using a Turtlebot 2 base, they all work with the same parallel to wheel. Okay, but if you have wheel base, for example, like you have robot that built on RC car, for example, then you might need to use the Ackermann steering. And also some of you might be using some other robots that have omnidirectional wheel or so on. Okay, so you need to identify what kind of wheel your robot design, and from there you need to know how to put in the appropriate model into your mapping program. Okay, right. And one key concept over here that I want you to just to expose you is this holonomic and non-holonomic. So holonomic is you can control all the degree, all the movement. For example, like an omnidirectional robot, you can move X, Y, and also theta. Theta means like, yeah, in a diagonal form, for example, independently. Okay, independently, which means you can move in X direction, Y direction, and also the theta direction independently. Then that is what we call the holonomic. But if your robot not able to do that, for example, our differential drive, we can actually move like forward, backward, sideways, and so on. But we need to turn in order to move in different direction. Okay, so which means it is some direction or some degree of freedom is actually dependent on other. Another example, for example, like Ackermann steering, for example, our bicycle or our car. If you want to go front and back, it's okay. But if you want to go sideways, you cannot do like that. You need to turn, right? So this is what we call it cannot move in all direction independently. So it is non-holonomic design. And in most of the cases, we are actually dealing with robot with non-holonomic robots or design, unless you are using, for example, the omnidirectional wheel. Then the chances is you have a holonomic design. And for holonomic design, they have its own control system, although it is more flexible, but the control might be more complicated. As I said just now, your parallel two wheel is just two control parameters. So it is very simple, but it is non-holonomic. Okay, so you can't really like do the side parking like this. Okay. So in order for you to understand the SLAM simultaneously localization mapping, okay, SLAM, in order for you to understand that, two key concepts that you need to understand first over here that I would like to explain in brief, because this can be explained like in a very long lecture, but I try to tell you the important point. Okay, so over here, the two concepts is, one is the odometry. So what is odometry? Odometry is the use of data from moving sensor to estimate change in position over time. Okay, which means, for example, if you are riding a bicycle, okay, you are riding a bicycle, you know what is your wheel size, and you know your traveling speed. Okay, and also you know like the angle that you steer. Okay, so if you know all these parameter as you move, you can actually calculate the distance that you have traveled. Okay, why? Okay, simple maths. You have the wheel, right? And then you have the traveling speed. Then with that wheel size or the radius or the diameter or the radius, you can times the speed, and then you know how much it has turned, right? Okay, you can calculate the circumference and so on. So you know the distance travel. By maths, you can calculate that. So by doing that calculation is what we call odometry. Okay, so you put a sensor on your wheel to calculate what is the number of rotation you have made over the time. Then you roughly know like how far you have gone. And also you put a sensor to measure your steering, for example, your steering, and you know what angle that you put in over the time. Then you can calculate eventually, like for example, after you cycle for like half an hour, where are you? Or how far you've traveled. Okay, so this is, if you do this calculation, this is odometry. Okay, so odometry is used by some robots, whether it's legged or wheel, it doesn't matter, because for example, like a very easy to understand example is, for example, human. Okay, you know, like when we use our phone, or we hold our phone and then we move, for example, like we walk or even we travel by car and so on, your phone actually able to tell you the location, right? So it is because it has the sensor in the phone, the accelerometer, and also some other sensor, that it can actually do the calculation to get the odometry. That's why your phone actually can know your position, right? So the same concept. So whether it's a wheel or leg, it doesn't matter. A lot of way can calculate this. Okay, so it's not just about calculating the wheel and so on, but sometimes we can use the speed, because you integrate the acceleration, you get the speed. You integrate the speed, you get the distance travel. Okay, so all this calculation is for under autometry to find your distance travel. Right. So in the robot, so I need to use one robot to explain this concept. So I use the Turtlebot. So in Turtlebot, we have the autometry, okay, because the Turtlebot itself got a gyro. Gyro basically is the sensor in the robot that very similar like the sensor in your phone. Okay, so your phone also have something, some sensor like the gyroscope. Okay, then we have the software to calculate the robot pose EKF. So what is this robot pose EKF? It's basically the Kalman filter, extended Kalman filter. So this Kalman filter thing, it used the gyro data and also the odom data. Odom data here means the odometry data. Okay, so the odometry data and also the gyro data. So the odometry is calculated by, for example, like your footstep. Then the gyro is, for example, the sensor in your phone. So you combine these two sets of data into your Kalman filter node, then it will start to calculate a more accurate odometry combine. Okay, so this is how it do the calculation. Of course, I won't be telling you how it do the calculation. Okay, but you can read more, because if you go to the next one, it says extended Kalman filter, EKF is the extended Kalman filter. So extended Kalman filter use measurement observed over time that containing noise and other inaccuracy, because like if you calculate your footstep, for example, you have friction, you have slip. Okay, so that is the noise and inaccuracy. And also your sensor also will have noise and inaccuracy. So these two sets of data, when you put together, you use the Kalman filter, it will try to give you or estimate the value that tends to be closer to the true value. Okay, but Kalman filter is a very, how to say, popular and important thing in mobile robots. So if you're interested, feel free to go to the Wikipedia to read more about it. But the concept is we use this Kalman filter to actually combine these two sets of data to find out a more accurate odometry result. Okay. Okay, so now we know how to actually calculate how much a robot travel based on over the time. Okay, so based on the speed, based on the sensor data and so on. So with that, why we want to do that is because we want to achieve what we call localization. Localization means you know exactly where you are at a given time in a given space. Okay, so for example, like I always use this example. When you want to use a map, or when you, for example, you go to when you enter an airport, for example, or a shopping mall, then you want to you have no idea how for example, like you go to a new airport, then you want to go to one of the terminal, but you don't know where is it. So one of the easiest way is you look at the map, right? There's a directory. Okay, so you go to the counter, you look at the directory, you look at the map, and it will show you where is the terminal. But the first thing you want to find out is where are you in the map, correct? You always find you are here, okay, in the map. So that is the first point that you are going to observe when you are using a map. You need to know where the time you are holding the map, where are you with respect to the map. Okay, so this is what we call localization. So robot, the same thing. In order for the robot to use the map for navigation, the robot need to know always where is the robot in the map. Okay, so how to do that? So this is what we call the localization. So how we do the localization is like, for example, for robot, it used the odometry and laser scan data. Okay, so first it used the odometry data, which is previously I have mentioned. So which means, for example, you enter the map, then you know, okay, this is the entrance. So you start from that point. Then after that, you calculate your odometry. Then you know roughly how much you have traveled. Then you use the distance and look back the map. Then you can pinpoint like where you have gone, right? Okay, so that is using the odometry. But of course, this is very rough estimation because like a lot of noise, as I say just now. So you also need to use your sensor, which means every time when you move around, you have to look around to check if your location is correct. Okay, right? It is very similar like you walk in a mall, right? you always like you go to a corner, then your friend said, okay, so after you move here, then you'll see what shop. Okay, so that is you're using your sensor to find certain landmarks. So it's the same. So robot will do the same as well. So you use the laser scan to scan the changing the changes of the environment. Right. So for example, we try to imagine the robot in a living room. Okay, so the picture on the right hand side is the 3D world, and then the map is on the left hand side. So this is the map. So the map is actually when you look from the top, okay, downwards for the living room. Okay, so you will see something like that. And you can see the 3 big block, that is the 3 cushion sofa, right? Sofa. Okay, so that is okay. But we know in the center, we have a coffee table there. But why in the map you only have 4 dots? You know why? It's because, just now I said, our map is a 2D map. So you only have 1 plane. And then if you look at the robot, the sensor is actually somewhere in the middle. So it can only see if you do a cross section, for example, you cut the living room, you can only see for example, like this is the table, okay? This is the table like this. If you cut like this, you can only see the leg, right? Yeah, it's because you do the cross section, you only see 1 plane. So that's why you can see the 4 dots. And this is also very important. Later, when you do your mapping, you will face this kind of problem if you have 3D object. For example, you have like a very long, a very tall table or chair that you can only see the middle, not the whole surface. So that will give you this kind of data. And what you need to do is in post-processing, you're supposed to draw a square to cover the 4 dots so that it become the region that the robot can enter, because yeah, the robot cannot collide into the table. So you have to specify that region to be not accessible, right? Okay, so this is how we do the map and the concept of the map, right? So the map basically tell the robot black color is you cannot go into it, but white color is something that you can travel. So white color is a free space, right? And then later on, you can see like in ROS, when we do in the RVs, we have gray color. Gray color is unknown, or the robot haven't scanned actually. So you actually 3 colors, but over here we only have 2 colors. But later on you will see like 3 colors. So white is definitely can travel. Black is obstacle or wall or something that you cannot travel, and gray is something that unknown. Okay. Right. So now, just now we have the odometry. So now we want to add the sensor data, the laser scan, right? So you can see like we add the sensor data on below. So over here, we use the Kinect sensor, which is similar like Astra sensor or whatever sensor that give you the laser scan, RP radar and so on. So this sensor data will give you your laser scan, and this one you will combine with your map. So you can see down there, there's a box called AMCL. So this AMCL is the software that we're going to use to help us to do localization. So the input of this software is you need to have the map, you need to have the laser scan, which is from the sensor. So these 2 data you can provide. And one more is what we call the TF. So where's this TF come from? You can look from on top. So on top, from the 2 set, the odometry and also the gyroscope or the IMU sensor data, you use the post EKF, the common filter, to get your TF from the Odom combine. Okay, so this TF basically is the way how ROS tell you the relationship between different module. For example, like it will have different frame of reference. For example, every part in your robot, they have its own origin. For example, your sensor, your wheel, and your mobile base, they have its own origin. So how to tell the relationship between these two is we are using the TF system. Okay, so the TF will tell you with respect to the sensor, the wheel is supposed to be over here and so on. So it gives you the location of the robots. So this information will feed into the MCL, and eventually we will know we can do the navigation, or we know the robot location with respect to the whole map. Then we can do the localization. Okay, so this is basically the whole concept. Right, I don't want to spend too much time on this, but later on you can read by yourself. Another important thing that I want you to read over here, if you want to know exactly like how this thing works, is just now I mentioned the AMCL. Okay, so AMCL is Adaptive Multicolor Localization. So this is a very, how to say, I would say it's a very smart way to do localization based on the sensor data or based on whatever information that we have in order to get. So it's very different from how human actually think about this. Okay, so when human want to do the localization, we actually look around and look at the map and see. But this concept is very similar, like the in adaptive multicolor localization. Okay, so this AMCL, what it do is it figuring out where the robot will need to be on the map in order for its laser scan to make sense. So for example, if your laser scan tell you in front got a wall, okay, so you open up your map and you pinpoint or you plot down all the possible location of the robot that when the robot is at that particular location, when it's scanned forward, it's supposed to have an obstacle or wall. So by initial guessing, if you have only one set of one sensor data, so you take out the map and then you plot all the possible location. So it's something like you put a lot of particles. So that's why later when you look at the AMCL in Alvis, you can see a lot of tiny arrow, because that is the initial guess of the AMCL that where you're supposed to be. But as you move, because your data gets increased, because like when I say, okay, my first step, I can see in front is obstacle. Then my second step is in front is not an obstacle, but a space. Then the third step to the left is I saw another obstacle. So if you have this data in a series, then in your map, you also can update. The first step, you can see, okay, the first step, these are, for example, you have 100 points that possible. Then on the second step, within this 100 point, which of the 100 point that don't follow the second step, you will remove the point. So you will have, like, for example, from 100, then as you go on, then it decrease until the end, you only have 1 point, and that is the point of your localization, because it fulfills all your sensor data throughout the time. So this way of doing is what we call the particle filter. So this is used in AMCL to do the localization. But of course, my explanation here might be not so good. You might don't able to understand. You can head to the YouTube or head to the Wikipedia to read more about this. Okay, it's a very interesting concept. Right. So I have explained basically the idea or the concept. I haven't actually touched any equation or calculation or any maths about it. It's just the concept. So I already briefly explained to you the concept behind when we want to do SLAM. Okay, so simultaneously localization and mapping. So you do your localization and then you gather all the sensor data, and your sensor data actually able to draw the map out. Because as you move, you know your position and you collect the sensor data and you put it down into a 2D plane, and that is your map. So this is what SLAM is all about, the concept. Okay, so so if you want to know more about the mathematical behind this, or the software, how we actually, the algorithm, how we actually do the SLAM and so on, you can go to this website, the open. So we are using this Gmapping, which is one of the very famous tool in building building map or SLAM. But of course, you got other way. Okay, for example, like Google Cartography and other stuff, RBT, I cannot remember, but there are many ways, okay, to do it. But we follow this ROS, this Gmapping, which is in ROS navigation. It's very stable. We use it and it's good. But this one is good for indoor. Okay, so if you are using, for example, like if you build robot for outdoor application, where you got very, very big space surface. For example, like you want to scan the whole forest, for example, and so on. Gmapping might be not that good. Okay, right. Gmapping is good for indoor with very tiny spaces. You got a lot of object that your sensor range is not very far. For example, like within 10 meters, you have a lot of obstacle, a lot of what we call wall and also door and so on. So it's very ideal for indoor mapping. Okay, so for example, you want to map, for example, your school, your university, your campus, or a mall, offices. This method is quite okay. I would think like it's good. But if you want to do outdoor mapping, where you have like more than 50 meters wide space that you don't have any wall and so on, you might want to use other thing. Okay, for example, we have one we call the Hector Spam, which is good for that outdoor application and so on. So over here, we introduce some tools that we focus on our application or our robot development, which is for service robot. So service robot, mainly it operate in a closed and indoor environment with a lot of small spaces. So this approach is what we introduce here. Okay, so you can head to the OpenSlab website to read more about Gmapping. So what is the algorithm for it to build the map from the sensor data? And you can go to the ROS wiki to read the wrapper. So how the ROS community actually wrap the Gmapping algorithm into ROS so that we can use it. And below there, there's a link, although this link is a bit old because it's the Indigo version, but the concept, everything is basically the same. Okay, until like the recent version, we are still using the same concept, the same tools actually. Okay, so this SLAM map building for Turtlebot, if you go to that site, you can see the steps how to do use a Turtlebot to build the map. Okay, but we are going to show you the demo. Okay, after this. Right. So before we start to show the demo how to do it, I would like to introduce you another tools, because today we work with something without robots, so you don't have a physical robot. So we can use this Gazebo Simulator to provide us a virtual environment. Okay, because if you want to do the navigation, you need an environment and also the robot in order to do the mapping, right? So this Gazebo Simulator in ROS provide us the environment and also the robot model. Okay, so it can give you the interaction between the robot and also the environment, and with that we can put the sensor in, move the robot around, obtain the sensor data, and draw a map. So that is how we do the ROS the navigation in simulation. Okay, so this is a very, how to say, handy thing, is because like for Turtlebot 2, it got its own simulation model. Okay, so you can, if you want to read more about Turtlebot simulation model, you can go to this ROS wiki site, which is to tell you the Turtlebot model in Gazebo. Okay, so I'm going to show you this. Okay. So let me switch to my another PC. Okay, so I will share this screen. Okay, so you can see my screen here. So I have my, okay, so let me show you my desktop first. Okay, so I have my desktop here. Okay, let me bring up, okay, the material over here. So we are talking about. So first, to show you the material first. So just now, where are we? Okay, over here. Right. So before we start our navigation development, first we need to create the robot model, because we want to do it in simulation. So we need to create the robot model and also the environment. Okay, and this Gazebo, basically this Turtlebot simulator, the simulation model of Turtlebot in Gazebo basically give us the environment and also the Turtlebot model. And if you install the Turtlebot, ROS package, you basically have this whole thing. Okay, so first I run my, okay, so this is my virtual desktop. Okay, so I use my virtual desktop, and today I try to put it full screen because like you need to see the whole thing. Okay, and it can run full screen like this. Full screen is like this. Okay, so you have the full screen. Oops. Okay. Okay, I need to put it back. Okay, yeah, this is annoying. It basically cover the top part. Okay, so try not to put full screen. Okay, right. Okay, so I've opened this thing up. So first thing is I need to run the Gazebo, right? So from here, ROS launch Turtlebot. So it's in the Turtlebot Gazebo model. Turtlebot Gazebo package, okay? Turtlebot Gazebo package. And inside there, you have what we call the Turtlebot world launch. Okay, so this is, it create the world, and also you have the Turtlebot. Okay, so let me run this. Okay, then it will run everything like the ROS core and so, oops. I hope it don't give me any error. Is it okay? Okay, so I have this. Okay, I need to make this smaller. I want to see what is the problem with this. I'm not sure if this is any problem, but let me run again. I don't. Okay, I will try again. Go on. Okay, let's try again. Should be fine. Okay, this time it's okay. Ah. Okay, it doesn't matter. I think it should be okay. As long as you can see the result. I don't know what is the error, but maybe later on I will check on it. Okay, so this is Gazebo with our 3D world. Okay, let me show you the whole thing. Okay, I need to. Okay, you can turn it. It's a 3D environment. But pull it down a bit. Turn it. You can turn it. Okay, and then over here. Okay, so maybe I zoom it in a bit so that you can see the Turtlebot. Okay, so this is the Turtlebot. Okay, turn a bit like this. Maybe this is better. Okay, this is better. Okay, you can see from here. This is the Turtlebot. Put it a bit in, and you can see there is an Astra over here. Okay, so which means the robot, the sensor will be somewhere in the middle. Okay, so this is the plane that, this is the plane. So this is the Turtlebot, and then this is the sensor. So the sensor will scan and give the laser scan at this plane. So you will build the map at this height. Okay, at this height, just like the one in the slide just now. So you try to imagine like all this obstacle, it will cut at this height. Okay, so it will cut this height, and then it give you the map. Okay, so that is the map that we want to build. So how to build the map? So with this Gazebo, we basically have the environment, which is we have the infinite world with several obstacles. For example, this is the obstacles, or we can consider this is the wall. Okay, for example. Okay, so let me put in a. Okay, maybe this one, it looks better in this way. Oops. Okay, like this. Okay, so you know this is a 3D thing. Okay, so you already saw it, but let me put it in a 2D form so that you can later on correspondent this to the 2D map. Okay, so I'll put it like this. Okay, so I close this. Okay, put this thing smaller. I need to optimize because like later on you have a lot of windows. Okay, I'll put this thing here. Okay, make this a bit smaller, a bit longer this side. Okay. All right. Okay. So maybe this one a bit higher. Still try to resize so that it looks nicer. It's harder to move this. Okay. Turn this a bit so that you can imagine. Okay, maybe I need to slide it a bit. Okay, so that you can see it is actually 3D. Okay. Okay, right. So this is good. So I've run this. So the second thing that I need to run, okay, I need to put this thing back. Okay, the next thing I need to do is to run the Gmapping demo, right? Gmapping demo. So I'm going to run the Gmapping demo. Open up another terminal. ROS launch TurtleBot. So under the same package, got the Gmapping demo. So this is a demonstration for the Gmapping tools. Launch, run this. So now I run the Gmapping. Okay, so the Gmapping, just now I said the Gmapping, the idea, the objective is to build the map. Okay, so it need to get the data from the sensors and so on. Done. Done. The Gmapping. Let me make it smaller. It's too big. Okay. So this full screen is not good. Basically, it just become very, very big. Okay, so Gmapping. Okay, so I've done the Gmapping. So the third step is to run the RVs. Okay, so why we need to do the RVs is because we want to see the sensor data. Okay, over here just now I explained you have the TurtleBot and have the RGBD sensor, but over here we are taking the laser scan. So we have a package in ROS that convert the scan in convert the sensor data, the RGBD data into the laser scan. Okay, so we use that. That I actually show you like last week, if I'm not mistaken, the laser scan, right? If you still remember. Okay, so over here it actually scanned in front, and because it's not visible here, but this is you consider this is the physical world, although it's virtual, but this is the real world. So this one is equivalent to the real environment and the real robot. Okay, and then the sensor currently is scanning, and you're supposed to get some data over here, right? Okay, so in order to see the data over here, we run the RVs. Okay, so the RVs is run by this. So it's ROS launch. It's TurtleBot RVs launcher view on navigation. Okay, dot launch. Okay, right. So with this one, we run the RVs. So you will see another window is popping up. Okay. I'm moving things around so that you have enough space to see things. Okay, so run the RVs. But over here, I just want to say this one is using the actual, how to say, this can actually get the sensor data from the real world. Okay. But over here we need to wait. How come I have? Oh, okay. I think I forgot something. Oh no. How come the robot model is not here? Oh, it don't have the robot model. Wait, something is not right. Something is not right. Okay, I think that is the error just now. Okay, sorry, but let me run again. I think it's this is the problem. Maybe let me restart my virtual system. Okay, let me restart this. Okay, let me restart this. And I'm using another server. Okay, I'm using another one. Because it seems like it cannot get the robot model. Okay, never mind. I'll try another one. Hope it's okay. Hope this is okay. ROS launch, turtle bot, simple. Yeah, I hope this is okay. Okay, yeah, this one looks okay. I'm not sure what is the problem, but yeah, later I will look at it. Okay, so close this thing, make this smaller. Okay, so this is the same model. I just changed another server to show you. Okay, so this is the same thing. Let's make it bigger so that you can see it. Okay. Okay, right. So this is good. You don't have the error. I don't know why just now the error, but well. The second one is Gazebo and then Gmapping, right? Okay. Okay. First scan, yes, good. Okay, apparently this is okay. I just don't know why just now got the problem, but anyway. Ooh. Cross launch. The third one is the RVs. RVs. View. Navigation. Launch. Okay. So I'll run the RVs. This time should be okay. Just now RVs informed that it cannot get the robot model. Okay, so hopefully this one can get the robot model. Okay, yeah, it seems okay. You have the robot model. Okay, but I still can find one warning here, which is the cost map. Okay, so because this one, this RVs, this setting is used to view the real robot, which means the sensor data is actually coming from the real world, real sensor and so on. So we need to change so that it replace with the simulation model. So over here, the first one is this topic. Instead of the real world cost map, you change to the virtual one. Okay, because the Turtlebot simulator actually provides this. Okay, so first you change this for local map and also for the global map. You change this to this map. Okay, then everything is okay without any warning and everything looks good. Right, so let me rescale this a bit so that you can see clearly. Okay, so just to put at the side here, get smaller here, and also maybe this one, make it bigger. Okay, right. I want to see this. This one I can put right. So let me turn this into the same orientation so that it's easier for you to. Okay, one way to identify the direction is this one. This sticker, the Turtlebot sticker, this one is showing the arrow. This is actually the turtle to showing the orientation. So this way, and also from here, you can actually see the same sticker here. Okay, so with this sticker, you can align it so that it looks the same, or it looks in the same direction. Okay, so somewhere like this. Okay, make this thing smaller. Okay, so now on the left-hand side is my simulated world that represent the physical robot and also the environment. Okay, so you can see this is a 3D display of the robot 3D and with the obstacle 3D. And this one is the 2D map. Okay, so you want to build the 2D map from here. Okay, put it smaller so that you can see. Okay, so now I want to do the mapping. Okay, so just now I have run all this thing. So now I need to move the robot around in order to build the map. Okay, let me see if I am following the correct step. Okay, so after I change this, then the third step is to turn on the teleop, and then I can scan the map and save this map. Okay. So now I turn the teleop, cross launch, Turtlebot, teleop, keyboard. Come on. Okay, so this teleop means I can use the keyboard to move the robot around. Okay, later you can see it actually show the key. Okay, so the key is this key. So I will use the I, the J, the L, and also the comma for front, left turn, right turn, and also reverse if I want. Okay, so this is the key. Right. So now I'm going to use this to move the robot around. Doesn't matter, so I'll put it down because I already remember the key. So please look over here. So I'm going to use this one to control the robot to move around, and you can see in RVs, it will start building the map. Okay, so let's see. So now I want to move the robot around. So you can see if I go downwards. Okay, so I move forward, then you can see the robot is actually turning, starting to. Maybe I need to turn to show you it scan the cabinet. Can you see on the left-hand side as I move, it got the scan. But because this is using the Astra sensor, so the scan or the laser scan is actually not so powerful. Later, Jupiter will show you the RP, which is the laser, the LiDAR sensor, and the scanning is actually much better. But anyway, I'll just move around here to show you how I build the net. So as you can see, as the robot moving, I start to collect the data, and it is showing in my RVs. So this is the process. I am scanning, collecting the data, and build the map. Okay, so Gmapping basically try to process the data and show you the map in Orbis. So can you see as I move past, the sensor pick up the shape of the obstacle, and then I slowly have the map. And you can see that the gray color zone is basically a white color zone. Okay, the white, the unscanned place is the gray color zone actually, right? And then the black color is the obstacle. So anything with the black color is what we call not accessible space. So can you see? So this is how we scan the map. So if you have, like, for example, Roomba or any floor cleaning robot that have the map building features, you will see something very similar, right? Yeah, so you need to be very patient to build this map, move around to get all the information in order for you to save the map. But I'm going to speed this because I already done the map beforehand. You need to spend quite some time to do the scanning because now I move very fast and you can see the scanning is actually not picking up that fast, right? You can see, like, yeah, because I'm speeding and moving the robot too fast. So the Kinect sensor is actually not so good. It don't give very good data. So that's why you can see the scan is not very nice, but it will update slowly. And so if it didn't update, that means I need to scan several times for a particular area in order for it to create the scan. And you can see if I move too fast, the odom start to be not so accurate. And you can see the round is not really round anymore. Right. Okay. But anyway, you got the idea. So this is what I need to do is I need to spend, like, for example, an hour just to move in all the corners, slowly scan everything. Or I can change another sensor. I put the RP LiDAR in or any LiDAR sensor in, then the scanning will be better. Okay, later I'll leave it for Jupiter to show you their scan. Their scan is much better because if you use a laser sensor, the scanning actually gives you better result. But anyway, the concept is the same, the procedure is the same. So just assume now I already like finished cover the whole area and I already have the map, for example. Okay, so the next step I need to do is I need to save the map. Okay, so if you open up your slides, so you can see after I finish moving around and I'm satisfied, for example, okay, just assume I have a good scan here. Okay, for example, just for safe time, I'm going to skip this. So just imagine that I already have a good scan in Arvis. So now I need to do the map. I need to save the map. So I'm going to do this. Okay, so I'll take out my terminal. Right, then I will open up and then I will say to ROS run map server map saver. Okay, please notice that they are different things, server and saver. Okay, then F, okay, home. So this is where to save your map. Home, username for my one is RF. So this one is for your home directory. And then my map, for example, maybe I change another name like map, class map, for example, like class map. Okay, because I'm doing class now. So I save this just to show you I save the map. Okay, right. I'm not going to use this map anyway. Okay, so I save this. Then I got the map. Okay, so it say, okay, I built a map and done, right? And done. Okay, so let me show you where is the map and how does it look like. So if you open up your browser, sorry, your Explorer, you can see the map is over here, class map, and two files are generated. The first one is the class map.pgm, which is this is the image. Okay, I don't have anything to show. Graphic, is it okay? Can I use this? I'm not sure if I can use this to see, but hopefully you can. Oh yes, you can. No. Okay. Apparently, like I don't have. Later on, I need to download another software to show you the file. Okay, it is. I can actually install Gm in this environment in order to. But you can open with any image editor. It is a graphic file. Okay. Basically, it's just a bitmap file, which is you have black and white and gray. Okay, but you can actually see the preview, right? I cannot make it bigger, but yeah, you can see the preview is gray color, and then you got some white color in between. It's the same as this. So it's this image file. Then you have another file which is come together. So this is the meta file, the YAM file. It have contained the information of where is the PGM file. So if you change the name or change the location, you make sure you update this. And then you got, like, for example, the resolution, where is the origin, and other parameters. Okay, so this is just the meta file, but it comes in this set. So make sure you have this, then only consider you have completed saving the file. Okay, so you make sure you have this too. So for the post-processing, you just need to modify this. You open this PGM file, which is just an image file you can open with any software for imaging. All you need to do is you need to correct it. For example, just now the 4 point that I say, you need to like make the whole thing become a big black box, so that to tell the robot that area you cannot enter. Okay, so it's just like a paint. Okay, you can paint it black, and the robot will know. Okay, so that area is not accessible and so on. Okay, so just to show you the map. Okay, so now already done for my Gmapping. So the mapping is already done. Okay, up to this point, I already done the first half. Okay, the second half is I'm going to use this map for navigation, but that one I will keep it for second half. Right. Okay, so I have done for my part. So I would like to, if you have any question, yeah, you may want to ask, or else I can invite Jupyter Robot to show us the same thing, but on the on the real robot. Do you have anything you want to ask? Any question? Basically, I have covered. Yeah, done. Okay, so if you have no question, then let me explain a little bit and invite Jupyter Robot to show you. So over here, what we can do is like we can compare the mapping in simulation and the mapping in real world. And Jupyter Robot actually have one example that maybe later on they can show. They can build. They have a model which they model the same as their testing ground in their office. So you can see I actually put up the raw gazebo images and also the real environment, which is that one is actually located inside Jupyter Robot office. So they got a test corner. They use the panel, the partition to partition out like a living room, and they create the same 1-to-1 scale gazebo model. Okay, so they can actually show you. They can build the map in the simulation and also in the real world, and the map obtained can actually usable in either real world and simulation. Okay, because for example, the map that built in the real world, they can use it for the gazebo simulation, and also the map that they built on gazebo world, they can actually use it on the real world. Because the accuracy is really very close. Okay, right. So let me invite Jupyter Robot to show you this demonstration. Is that okay? Max, are you there? Max, are you there? Or Huang, Dan? Jupyter Robot, are you there? Is Jupyter Robot with us? Yeah, Max. are you there? Hello. Okay, I can't hear you. Max, I can't hear you.
Oh, okay.
Okay, yes. Okay, good, good. All right.
Yeah.
Okay, so now you might want to take the, okay, yes. Okay, so now let's let Jupyter Robot to show us the Gmapping example in real robot.
Okay.
Yes.
This desktop is from the computer of our real robot.
Okay, all right. Okay, so they are running. Okay, so you can see, let me explain a bit. Like you can see the robot, which is at the same office that I showed just now, and at the same location, the starting point. And currently the desktop belongs to the desktop of that robot. Okay, good. So now Jupyter Robot is going to show you how they can remote control. So just now I used the teleop, right? So they use the remote control way to remote control the robot so that you can see the scan updated in Arvis. Okay, so
first, we bring up our robot.
Okay, so you bring up. Okay, so because now this is the real robot demonstration, so they need to bring up the robot. They need to start the robot.
Yeah. Then we launch the Gmapping in our Jupyter Robot Gazebo.
Okay,
yes.
So you can see the step is very similar. So just now our first step is to run the Gazebo for our virtual world, but now because it takes place in the real world, it start the robot, right? Then the second step just now I run is the Gmapping demo, and they also run the Gmapping demo. Basically, they use the same Gmapping demo. Okay, so we use the same Gmapping software to do the mapping.
It's navigation. Yeah.
Okay.
Okay. Here, odometer received means yeah.
Okay, which means the Gmapping have received the odometry from the robot. Then it run the RVs. So similarly, it also use the RVs to show you the sensor data and also the map building. So you can see Jupyter Robot and the Turtlebot, they are using very similar tools to achieve the same objective. And currently they are using the RP LiDAR sensor. So you can see the scan is much better. I mean, the response is much better as compared to the Astra sensor.
Yes. Last the
Teleop.
What? Yeah, teleop.
Yeah. You.
Use
you're using
joystick.
the joystick. Okay, so Jupyter Robot is using the joystick. Okay.
Yeah.
Right. So the next is they will move the robot around to show you the scan. You can see the update of the RVs is very smooth because the sensor data is much better from the LiDAR as compared to the RGBD sensor.
Because the laser can only scan one horizontal plane, so you can see this table, we can it can only scan for legs.
Yeah, so it's the same reason just now I said the laser scan basically is at a certain level, all right? So it's just a 2D plane. So if you are scanning a table, which is the face of the table is higher than the sensor, then you can only see the leg. So that's why you can see like the white table, it is actually not appear, but you can find 2 dots over there, right? The 2 dots indicate the 2 legs. So in post-processing, we need to connect the 2 dots so that it becomes a solid black color. Yeah, it's the same for the coffee table as well. Can you see the 4 dots over there? So that one require the post-processing. We need to open up the image and we need to darken, make the 4 dots become a solid square. Yeah, but you can see overall the scanning is very smooth and you can see very nice wall. The line is very straight. So yeah, a LiDAR is actually much better in terms of like mapping. Then yeah, it's using the same approach, using the map server tool and map saver node to save the map.
I'd like to.
Okay, so they are saving the map. Okay. Okay. So then can you show us the map where you saved?
Yeah.
Okay, over here, can you open up the BGM? Yes, the BGM. Okay, yeah. So you can see the PGM file is basically an image that similar to what you saw in Arvis. And what the post-processing need to do, then okay, show that. Is you can see when we scan the coffee table, we have the 4 dot. Then can you open it in Gym?
What?
Open in Gym. Can you draw the black color box for the 4 leg?
You mean edit the
yes,
image?
edit the image.
Okay.
Okay, so you can use, for example, like okay, then can use one tool. Yes, this GIMP. So this is an imaging software. Okay, you can use any imaging software, it doesn't matter. So it open up that file, and then the post-processing that need to be done is you need to connect the 4 dot and make it a solid square. And this one is the important post-processing to improve your map for certain thing that you cannot scan in real world. Yeah, it's like this. Yes, this is what I mean. So yeah, you can spend time to slowly draw later on. And then important thing is you need to make a boundary. Make sure you cover the whole thing so that the robot won't enter or will not try to do the path planning to enter the space. Okay, so this is what I mean. All right, thank you then.
Okay.
So this is what you need to do for post-processing when you have this kind of problem. Okay, right. So yeah, done. Okay, so done. We will start the second session, but let's wait for the next demo. Okay. For the time being, do you have any question you want to ask? Do you have any question, anyone? Then can you show the same demo but in Gazebo?
Okay.
Okay, so now let's compare. So just now, Dan did the whole thing using the real robot. So now let's try to do the same thing but in Gazebo, because they have the map, the Gazebo model of the real office, so they can actually do the same scanning with the Gazebo model as well.
Yeah.
So just to show you the comparison between real world and also the virtual world.
Okay.
Okay.
There are 2 world files in this folder, and I will.
Yeah, you use the Jupyter Robot Office.
Yeah.
Okay.
like
So you can specify the path to tell Gazebo where is the map file, or sorry, the world file. Okay, to create the world. Okay, so you can see this is the Gazebo model of the real office just now. So now we will repeat the same step and to scan the map. Okay, you can see it's almost the same, right? These two, except some like we don't have a nice texture to represent the sofa and so on. But important thing is we have all the obstacle, location, everything is the same. So it's okay, right? So please show the Gmapping.
oh yeah, the okay, is command. Yeah.
Okay, you got the scan.
The same view navigation.
Okay, so the same, we use the RVs as well.
Yeah.
For the visualization of the data in the map.
We can also use this joystick remote controller.
Oh, okay. Okay, so please move around. Okay, so you can see, let's then now try to move the virtual robot in Gazebo, and you can see the scan is also updating as compared to the real world. So yeah, it is the same. And we can see the map is building in RVs. So the same tool can be used to do the mapping, whether in real world or in simulation world. And if you have the Gazebo model that exactly like almost identical to the real world, you can actually do everything in simulation world, and it still gives you the same result. Yeah, so you can see like Max is using the joystick to control the robot in real world, but now he's actually sending the message from the joystick to control the virtual robot. So in ROS, the simulation and the real world, they have the same sensor and actuator model. That's why your as long as you give the same signal to either the real world or the simulation, it will behave the same. Yeah, apparently like it's a bit harder to control the simulation model. Maybe the real world is easier and you feel more realistic when we do the control. But nevertheless, you can see the map scanning is very smooth and it gives the same. Yeah, in fact, I think the scan in simulation is much accurate because you can see very few noise, very few noise.
Yeah, here, yep, it missed 2 boxes here because the scan plane is higher than the top of these 2 boxes.
Yeah, correct. So it behaved the same because it followed the physical, the real world phenomena, which is the scan only at that scan the sensor level. So anything lower than that, it actually cannot see. This is the limitation when we do a 2D SLAM. You can't really see things in 3D.
Yes. I can open this one to compare.
Yeah, so you can see the comparison between the scan from the real world and the scan from the simulation world. They are really close to each other. They're almost identical. But what we can notice is like the noise in simulation world is much lower as compared to the real, which is, it makes sense because real world got more noise and other thing. But important thing is we can actually do the navigation development in simulation world and give us very close result to the real world. Yeah. Okay. All right. Thanks. Okay. Thanks. So we will take a break from here, and then we will proceed to the next session. Okay. We'll proceed to the next half of today. Okay. So while I'm switching to the second part, do you have any question you would like to ask? I would like to invite our LOC maybe to ask also the audience in Thai to see if they have any question they want to ask.
มีใครมีคำถามไหมครับ
Yes. Do you have any question you want to ask?
I want to know about spec of computer for run everything like this simulation and Gmapping.
You mean the computer spec? Is it you having problem to run on your computer?
Sometimes it's slow in Gazebo, something like that.
Okay, so just to tell you, like I think like my desktop should be not a problem, but I can tell you like when I run on the virtual desktop is like very minimum resources that I can provide. I think it's about like a 2-core CPU with about 4 gig of RAM, and don't have any graphic card actually. and it works. So I'm not sure like what is the spec of your PC that will give you the problem. Do you have a spec which is lower than what I just said? Or you are using a VMware or a VirtualBox? Are you using VMware or VirtualBox?
I have problem with VMware, but in real computer I don't have problem.
Yes. So what I can say is when you are using VMware or VirtualBox, the resources that you can give sometimes is very, very low. Maybe lower than what I just said. 2 CPU or 2-core CPU with 4 gig of RAM. If lower than that, I think it might be hard for you to run the simulation. So that's why I don't really I will recommend you not to use VMware or VirtualBox unless you have very powerful machine. Yeah, that is the reality, that you need a lot of resources especially when you run Gazebo and you run RVs together. So both require a lot of resources to run. So when you use some VMware or VirtualBox, unless your machine is very powerful and you can give a lot of resources to your VMware or VirtualBox, which is I think the minimum that you try supposed to give like 2 CPU with 4 gig of RAM. If you cannot provide this, then maybe you cannot have very smooth simulation. So just now the example, of course, running on local machine, for example, like on Jupyter Robot or on local machine should not be a problem. But I show you like even when I run on the virtual desktop, it's still able to run without problem.
Thank you.
Yep. Any more other question?
Excuse me, Jeffrey.
Yes.
If he enable the graphic accelerator 3D, can help him. It can help this faster.
Oh, okay. Yeah, maybe. Yeah. So for VMware or VirtualBox, you can try to use the graphic accelerator, but I'm not sure how much it can help. Of course, you can try that. Yeah. So maybe you can try if you have a good graphic card that you can add in the support for your VirtualBox or your VMware. Maybe it might help in your rendering as well. So which means if you are using VirtualBox or VMware, try your best to provide more resources to your VirtualBox or VMware. Yeah, whether in terms of the CPU or the RAM or your graphic resources. So you might want to try with, thanks for the suggestion. Yeah, you try with the graphic accelerator. Okay, any more question? Okay, if no question, then I'll proceed to the next part. But before I go to the next part, this is the assignment for this. So I want everyone to use whether you're using any setup, okay, you're using a VirtualBox or VMware or dual boot or anything. Okay, so try to exercise on building the map, and then you post-processing the map with graphic editor software. You can save out and use your Photoshop. It doesn't matter, okay? Any image editor that can edit the PGM file, don't try to convert the format, because if you convert to JPEG or anything, you might have problem to put it back, okay? So try to find the editor that can open the PGM file directly. In Linux or in Ubuntu, you can install the software that just now Jupiter Robot showed you, the GIMP. The software you can install for free, and you can use that software. It's very similar like your Photoshop to edit. Okay, so try to learn also the post-processing map. Okay, and then determine waypoint at several key locations. This one I will show you in the next part. Okay, right. Okay, so let's go to the second part.